So in the previous video, we moved past our fourth hyperoperation called tetration and got into the fifth hyperoperation called pentation, which is even more ridiculous than that fourth one. And what I tried to do to really demonstrate the ridiculousness of this operation called pentation is I tried to do pentation with a 4 and a 2, which are relatively small numbers, but what you'll see is they have to be relatively small numbers to get anything out of it that's anywhere near something we can wrap our heads around. So what I want to do in this video is really show you, maybe impress upon you, the enormous size of the number that results if you do pentation with a 4 and a 2. In the last video, we calculated that to be, well, we didn't really calculate it to be anything. We said one way you could write it as 4 raised up to this ridiculous power. That doesn't really help. Maybe a better way to write it, a way that we'll reference more in this video, is as 10 raised up to this power, 8 times 10 to the 153rd power. And 10 raised up to 8 times 10 to the 153rd power is really hard to wrap your head around. Like, what does that even mean? So in this video, we're going to try to understand what that means. And the way we're going to do it is a little bit ridiculous, but stick with me. What we're going to do is we're going to program a computer, or we're going to suppose that somebody could program a computer to write one digit of this absurd number anytime someone on Earth clicks a pen. I was trying to think of something people could do really quickly, and I had a pen in front of me, and I started clicking it while I was thinking, because I do that when I like fidget a little bit. And then I was thinking, man, that's pretty quick. Maybe I can use that as my example. So that's what I ended up doing. Anytime anyone on Earth clicks a pen, this computer is going to write one digit of this number. So to be clear, we're not trying to click pens this many times. We're trying to click pens enough times so that the computer can just write the number. The pen clicks correspond with the length of this number, not the value of this number. So the way this is going to work is it's not just one person clicking pens to get this computer to write digits of this number. Everybody on Earth is going to click pens to get the computer to write digits of this number. And what I'm going to show you to try to impress you by the size of this number is show you that it's going to take a little while. And a little while might be a little bit of an understatement, but let's see. If we're going to figure out how long it would take for the computer to write the number, we need to know how quickly somebody can click a pen. So what I did is actually went up in my office and started clicking pens as quick as I could and try to time myself. And I think what I came up with is that 40 clicks in 10 seconds is pretty quick. You can try it on your own if you're interested, or you can just take my word for it. That 40 clicks in 10 seconds is pretty quick pace. I'm not saying nobody can go click quicker than that, but that's a pretty good pace. I'm going to suppose that everybody on Earth can keep a pace slightly quicker than that. 42.25 roughly speaking, clicks every 10 seconds. And we're going to keep that pace. So if we can do that every 10 seconds, we can multiply that number by 6 to figure out that a person would be able to do 253 and change every minute. And importantly, we're going to keep this pace indefinitely. This won't just be for 1 minute. This will be the pace that everybody on Earth will be assumed to be able to keep for as long as it takes to write this number. A few more assumptions that have to get out there. Everyone on Earth, except for me, is going to be working on this. I'm not going to do it because I kind of know the punchline to this whole thing, and I don't want to be clicking a pen that long, but everyone else is going to be doing it. And I'm just going to assume that they're really dedicated to this, and they're never going to stop to sleep or eat or do anything else. It's constant pen clicking. And this pace is going to stay constant at this somewhat weird-looking number, but whatever, let it slide. And nobody is going to die because I don't want to worry about that. I don't worry about people procreating or being born or dying or anything else. We're going to keep our population fixed. So, okay, I have a rate per minute. I guess I need to know how many minutes there are in a year. Well, there's 60 minutes in an hour and 24 hours in a day, and a little bit more than 365 days in a year to account for leap years and such. So if you multiply these three together, you figure out that there are roughly 500,000 minutes in a year. So if we have our pace of 253 or so clicks per minute, and we multiply that by the number of minutes per year, 525 give or take, we figure out that each person could complete, 133 million clicks per year. That's some dedication to click a pen 133 million times, but we're going to suppose that people are really into this and they're really trying to write this number and they're able to do this many pen clicks. This is per person, by the way. There's more than one person working on this. Recall everyone on Earth is working on this. When I checked Google or Wikipedia or something, it looked like there are roughly 7.5 billion people on Earth. So I'm going to assume that there's exactly 7.5 billion people on Earth and me, because remember, I'm not doing this. So each of these 7.5 billion people on Earth will be able to make 133 million clicks per year. That's a lot of clicks for humanity. We can multiply these two numbers together and figure out that humanity, if we were dedicated enough and we believed all these different assumptions that I'm telling you to assume, could do this many clicks per year. A quintillion, I believe, is what this number is. 10 to the 18th power digits per year is what humanity could do if we had a computer that could write digits of this number every single time somebody on Earth clicked a pen. And you're like, okay, cool, so we'd be done pretty quick, right? Nah. Remember, our number has 8 times 10 to the 153rd power digits. 10 to the 18th power is way smaller than 8 times 10 to the 153rd power. So we're not going to be done in a year. Like, all right, so we won't be done in a year. How long is it going to take? Well, quick aside, we got to talk about me, right? Because I said I'm not clicking the pen. So you might wonder, if you're not clicking the pen, what are you doing? Well, I got to do something. I got to find a way to entertain myself. It's a true story. I always want to go visit Mount Everest. I think that'd be kind of cool. Not really into climbing it, but go down to base camp or something would be really neat. But I can't go to Mount Everest because travel is impossible because everybody's just clicking their pens. But what if I brought Everest to me? I mean, I got a lot of time, right? I'm immortal too. I think that was one of the assumptions, is that everybody's immortal. So I got all the time in the world. Maybe I could bring Everest to me. Maybe I could genetically modify a species of ants, and I could teach these ants to go over to Nepal and get Everest for me. So we're going to suppose that I can do that. That's another assumption that I'm going to ask you to accept. What we're going to do is we're going to assume that I train these ants to walk from our school in Oregon all the way to Mount Everest with an ant wheelbarrow that I also designed, and they're going to bring me back 1 grain of dirt from Mount Everest. That's what these ants are going to do. It's worth pointing out, an assumption that we'll need later, is that a grain of dirt is roughly spherical with a radius of 0.2 millimeters. Maybe that seems about right. Maybe you just let it go. I got some bad news for you. I screwed up. Right? You were impressed when I genetically modified these ants. You thought that was pretty cool. But unfortunately, maybe I spent too much time on the genetic modification and not enough time on engineering, because I made the wheelbarrow that these ants are going to take to Mount Everest too heavy. It's so heavy, in fact, that it's only once every million years that one of my genetically modified ants comes along that is strong enough to move the wheelbarrow. It takes 1,000,000 years for an ant to come along that can even budge this heavy wheelbarrow. And when that ant does move the wheelbarrow, he can only move it 2.4 centimeters before dying. So let's let this play out a little bit. It's the year 1,000,000 and 2019, because I made these slides last year back in 2019. And what happens is this super strong ant called Anthony the Great comes along and pushes this wheelbarrow from my desk up in my office, where it currently is residing, 2.4 centimeters towards Mount Everest. So not very far, and then dies. And then the colony just hangs out there until 2,000,000, 2019, when another one of these super strong ants comes along and pushes the wheelbarrow another 2.4 centimeters towards Mount Everest. And then he dies. And this continues. And it's going to take a little while, because my office is right there, and Mount Everest is right there. And per Google Maps, that's about 12,000 kilometers away. That's a long way, especially when you're traveling at a not very fast rate of 2.4 centimeters every million years. If it's 12,000 kilometers to get to Mount Everest, and they only walk 2.4 centimeters per million years, well, let's see, 12,000 kilometers, I guess that would be 12 million meters, or 1.2 billion centimeters. If they're doing 2.4 centimeters every million years, that would mean I'd need 500 million of these special ants in order to get there. And these special ants only come around every million years, so it would take this many years. What is that, 500 trillion maybe? It would take me this many years for the ants to get to Mount Everest. But the goal wasn't just to get to Mount Everest, the goal was to come back to me. So it's going to take them that long to get back. So I need to double that amount of time. I get 10 to the 15th power years before the ants return to my office and present me with 1 grain of dirt from Mount Everest. This is the year when these ants return home. It's worth pointing out that this many years from now, our sun will long have since burnt out. There would be all sorts of changes to our planet. Everest wouldn't be there anymore. There's all sorts of problems with these assumptions, but let it slide. Not only will our sun be gone, all stars currently alive will be gone, but whatever. We're going to suppose that doesn't happen. We're going to suppose the ants keep marching and the people keep clicking. Think we're done? Think our computer's written the number? Got bad news for you. It's been 10 to the 15 years, and we do 10 to the 18th power digits per year. I multiply the two of those guys, and I get 10 to the 33rd power, which is really, really, really impressive. It's a lot of digits. It's way more digits than has been written by humanity in its history, by a long shot. But it's nowhere near the amount of digits that we need for this number. 10 to the 33rd power compared to 10 to the 153rd power, and then times 8. Is nowhere close when these ants get back. It's this year when these ants get back, and I don't want to appear ungrateful or anything, but I didn't really want 1 grain of dirt from Mount Everest. Right? I wanted Mount Everest. So what I tell the ants is, hey, thanks, appreciate you, leave the dirt right there, but why don't y'all head back to Mount Everest and go get me another grain of dirt? So they do. And every 10 to the 15 years, that's how long it takes a round trip from my office to Mount Everest if you're traveling at the pace of 2.4 centimeters every million years. Every 10 to the 15 years, they drop off another grain of dirt to me, who I'm king for some reason now, in hopes that they can eventually bring me all of Mount Everest. Wonder how long that will take. Well, I guess I'd need to know some stuff about Mount Everest. Let's do a couple Mount Everest assumptions. Apparently, per some Google image search, Mount Everest has a base that's about 6 kilometers wide. And I know that the height of Mount Everest is 8,848 meters. Let's go ahead and assume, to make the geometry easier, that Mount Everest is a cone. That's not at all really true, but it's a formula that I have memorized back from my geometry days that will allow me to calculate the volume of Mount Everest. If I assume that Mount Everest is a cone with this radius and this height, I can calculate its volume to be this ridiculous number, and I don't really want its volume in cubic meters, so I do a little bit of a conversion to figure out its volume in cubic millimeters. The reason I want that volume in cubic millimeters is, remember that a grain of dirt was spherical with the radius of 0.2 millimeters. And since I know the formula for the radius of a sphere, I can calculate the volume of a sphere, or namely 1 grain of dirt, to be this number. So if I have the volume of Mount Everest and I divide it by the volume of the grain of dirt, I can figure out how many grains of dirt Mount Everest is made up of. In other words, how many trips these ants would have to make to and from Mount Everest to bring Mount Everest to me. 10 to the 22nd power grains of dirt in Mount Everest by my rough calculations here. I need 10 to the 22nd power trips, and each trip lasts 10 to the 15 power years if I want these ants to transport Mount Everest to SOU. That's 10 to the 37 power years. That's a really, really long time. I had no way to even explain how long that was, so I figured I'd let Wikipedia do the trick. And what they said is, after the 10 to the 37 power years, half of all baryonic, I have no idea, matter will have been converted into gamma ray photons and leptons. That doesn't sound good. Sounds like pretty much everything's going to be gone. But whatever, I'm not too concerned about it. We're going to assume that everything's still here and that this process can continue. In 10 to the 37th power years, it'll be this year. Mount Everest arrives at school. Up in my office, I guess, is where it is. That's pretty exciting. I got my very own Mount Everest. Awesome. The sun's long since burnt out. All stars have long since burnt out. The whole universe is this vast sea of nothingness, but I have my very own Mount Everest. Awesome. Wonder how the clicking's going. Well, that's easy enough to calculate. It's been 10 to the 37th power years. We do 10 to the 18th clicks per year. It sounds like we have 10 to the 55th power clicks done. Okay, we're making progress, but not really. We got a long way to go. So what are we going to do next? Well, I don't know. I got nothing left to do. It was cool to see Everest and all, but now I feel like kind of a jerk because that was a big thing in Nepal and now it ain't there anymore. So I'm like, all right, I have my phone. Why don't you ants go ahead and bring Everest back to Nepal? So they turn around and grain by grain at their very, very sluggish pace with their overly heavy wheelbarrow, they bring Mount Everest back to Nepal. And it takes as long to get it back as it took to get there. So it's this year by the time they bring it all the way back to Nepal. And what I'm going to assume is that the grateful Nepalese government gives me this bill, $1 trillion bill. The reason I made it $1 trillion bill is because at one point I tried to calculate how much it would actually be worth, accounting for some constant inflation rate, but it wasn't even possible. No matter how low I made the inflation rate, this got down to basically zero. At any rate, they gave me a bill. And what I do with this bill is I'm like, all right, cool, thank you. And I just put it down on the ground. Because what else am I going to do with it? Can't buy nothing. Everybody's too busy clicking. It won't surprise you to hear that I'm nowhere near done. So I got to continue this process. So I put this $1 trillion bill on the ground. It's 0.1 millimeters thick, by the way, in case you're wondering how thick currency was. And I tell the ants to entertain themselves by bringing Everest back and forth from SOU all the way back to Nepal, all the way back to my office at SOU, all the way back to Nepal, and so forth. And I'm going to assume that every single time they get it all the way back to Nepal, I get another one of these $1 trillion bills. And what do I do with the $1 trillion bills as I get them? I just stack them up. I just put one on top of the other one. And I continue to do that. And I wait and I wait and I wait. And after I've earned 100 million of these bills, my stack will be 10 million millimeters high because each one is 0.1 millimeters thick. And 10 million millimeters high is 10,000 meters. After I've earned 100 million of these bills, one at a time by transporting Everest back and forth from Nepal to SOU, my stack of bills is taller than Everest itself. It's 10,000 meters tall. It's pretty impressive. 100 million of these bills, aka 10 to the 8th power of these bills, each taking 2 times 10 to the 37th power 2 times because I got to bring it back and forth to earn, means it's been 2 times 10 to the 45th power years. I can multiply that time by the number of clicks I have, and I figure out there's been 2 times 10 to the 63rd power clicks, still nowhere near our goal. So I don't stop. I keep stacking these bills, and I stack them and I stack them and I stack them until they get out into space. And I don't stop when I get to our sun or when I get to outer reaches of our solar system. I keep going until I get to Proxima Century. Proxima Century is the closest star to us other than our sun. It's 4.25 light years away. At least it's 4.25 light years away right now. It's not there anymore because now it's completely gone, but we're going to pretend it's still there, and I'm going to stack my dollars that I earn ever so slowly until they get to Proxima Century. 4.25 light years is roughly 5 times 10 to the 13th power kilometers, which I can convert into millimeters, which I can figure out how many bills it would take. And I know how long it takes me to earn 1 bill, so I can do a little bit of multiplication to figure out how long it'll take till my stack of bills reaches where Proxima Century used to be. If I know how long, I know how many clicks, 10 to the 76 power clicks, dang, still a long way to go. So we keep going. I get to Proxima Century and I'm like, all right, let's get rid of all these bills. That was kind of a mess. I throw them all into the void. Somehow I get rid of all of them. How? I don't know. How could there possibly be enough matter on Earth to create bills that would get you all the way there? I have no idea. Stop being so literal. We're just going to keep on going and assume this process can continue as long as we want. I get rid of all those bills and I start over. And I get my first bill from the Nepalese government and I put it back on the ground. And I continue to do that. And I want to keep track of how many times I reach Proxima Century with my stack of bills. So every time I reach Proxima Century, I pick an atom on Earth and I give it a name. What do I name it? I don't know. I got a long time to think about it, right? It takes a really long time for my stack of bills to reach Proxima Century, so I can be really creative with my atom names. Name them whatever I want. I pick an atom on Earth, I name it. When I finish every single atom on Earth, I move on to another planet in our solar system. And I start naming its atoms one by one every time I reach Proxima Century with my stack of bills. And then when I'm done with every single planet in our solar system and all the rest of the matter in our solar system, I pick another star in our galaxy and I name all of its atoms. And I continue to do so until I name every single atom in our galaxy. Not on Earth, not in our solar system, but in our galaxy. There are 10 to the 68th power atoms in our galaxy. I know how long it takes my stack of dollars to get to Proxima Century, so I know how long it takes me to name one atom. If I know how many atoms I have to name, I can multiply those together to figure out how long it would take, and then I can use the rate at which people are clicking to figure out how many clicks I have. Trust me, my clip count is up to 10 to the 144th power at this rate. What just happened? That got kind of weird. What was I even talking about here? Oh, right. There was some number that I created with pentation, right? Our 5th hyperoperation. And it didn't look that intimidating because I created it with just a 2 and a 4, relatively small numbers. But I was trying to make the case that even with small numbers, pentation, this 5th hyperoperation, gets so absurd that the numbers just get gigantic, mind-blowingly gigantic. And so what we wanted to do is not click a pen that number of times, but instead click a pen enough times so that a computer could just write that number. So it's not the value of that number we're going for, it's the length of that number, which is already a huge difference. But just to get to the length of that number, we had to go through some absurd steps. We had to have a quick pace of clicking these pens, and we had to have everybody on Earth working on this nonstop at a really quick clicking rate. And they had to do so for so long that in the amount of time that they were clicking, I was able to send ants to go pick up Mount Everest grain by grain from Nepal and bring it back to me, with the ants traveling at a speed of only 2.4 centimeters every million years. And after they brought me Mount Everest, I just had them bring it back to Nepal. And I kept track of how many times they brought it back to Nepal by stacking up dollars that this hypothetical Nepalese government gave me every time Mount Everest got back to Nepal. And these dollars that I stacked up, I kept stacking them until they reached Proxima Century, 4.25 light years away. And I wanted to keep track of how many times my stack reached Proxima Century. So what I did is I started naming atoms every time my stack of dollars reached Proxima Century. And I had enough time to name every single atom in our galaxy. This whole time, you and everybody on Earth is just clicking your pens at this really quick pace, and we've gotten up to 10 to the 144th power clicks. 144 is really close to 153, which maybe you remember was kind of our goal. But bad news, 10 to the 144th power is not close to 10 to the 153rd power. In fact, it's only this percentage of the way there. It's nowhere near there. Our number that we created with just a 4 and a 2 using this fifth operation of pentation is a number that is 8 times as long as a number with 10 to the 153rd digits. All that to say, this number is really, really big. And we're not even going to stop there. In the next video, we're going to look at numbers even bigger than that. In fact, we're going to have to get astronomically bigger than that if we want to get anywhere near Graham's number.